it relates to two important variables that we haven't really dealt with before, and that is two numerical variables. In other words, we've dealt with one numerical variable examined within groups, where we did either a t, we took, and what did we do? We took that numerical variable, we found the mean for each group, representing the mean for that population, and we compared group one to group two, and we did a t-test. We compare, if we had more than two groups, maybe ethnicities, and we were looking at income, we'd get the mean income for ethnicity one, ethnicity two, ethnicity three. We'd compare more than two means. And for that, we use analysis of variance. Then we looked at a situation where we might be looking at variables that were all categorical variables. For instance, if we wanted to look at whether the population, the prevalence of diabetes in different ethnic groups. Well, we'd be looking at ethnic group one with regard to yes or no, that person has diabetes. So our variable is ethnicity, and our other variable is whether or not a person has diabetes. Within ethnicity, we have five different possible values, let's say. Within diabetes, we have two values that have it or they don't have it. So we could all have situations where they're both binomial variables. For instance, asbestos exposure and lung cancer. In other words, variable one is asbestos exposure. One, they did have it. Two, they didn't have that exposure. And variable two could be lung cancer. Yes, they have had lung cancer. Or two, they didn't develop lung cancer. So we can compare those. And we use chi-square to examine whether the rates, the values in each one of the crosstab that we created were what we would have expected them to be if there was no relationship between the exposure, the asbestos, let's say, or ethnicity, and the outcome, the income, and the lung cancer. So we had a good tool for that. We also had, as a corollary, we also had the tool odds ratio and relative risk that we could use for categorical variables as well. Well, now the one other main situation that we haven't addressed is how do we look for a relationship between two numerical variables? Okay, so for instance, let's say I'm going to just pick up Levi's example. He was working with height and age. Let's say that height and weight, rather. Let's say that I'm going to change it a little bit. Let's say age and weight, right? People tend to gain weight as they get older, so we want to see if there's a relationship between age and weight. So you randomly select the population, and you measure each person's age, and you measure their weight, right? And you say to yourself, well, gee, younger people, like let's say this one person, his age is 21 and he weighs 150 pounds. Another person is 33 and he weighs 170 pounds, and so on and so forth. So we want to see if there's a relationship between the two, right? So for each individual, we have a value for age and we have a value for weight. Now, we can't just take the average age and compare it to the average weight. They're two different variables. We can't do a comparison of means there, can we? However, what we can do is we can plot it on a graph to examine if we think that there's some relationship between the two of them. So that graph that we're talking about is called a scatter plot, just a simple XY graph. Okay, and I'm gonna draw a quick one here. Okay, let's see. And well, let's stick with age. What the hell? Okay, I'm gonna make up all these. These are all made up numbers now. Okay, these are all adults. Okay, and the youngest person here is going to be, say, 20 years old, and this is going to be 30 years old, this is going to be 40 years old, this is going to be 50 years old, this is going to be 60 years old. Now, I put those on this axis. What axis is that usually called? That's the x-axis. Okay, a lot of times we'll use x to represent the independent or the predictor variable, and y we would call the dependent variable. Okay, and that's going to be weight. And I'm going to say, let's say this is 100 pounds, this is 150 pounds, this is 200 pounds. Okay, and that's going to be my dependent variable. In other words, I'm thinking that weight's not really a good predictor. I would not expect a person's weight to determine if once they're an adult. If you have a child, and weight might be kind of a good predictor of age, but with an adult, I'm more likely to see age as a predictor of weight than the other way around. Okay, so I'm gonna call the weight the dependent variable. It depends on how old you are. What your weight is, to some degree, depends on how old you are, because we all tend to gain weight as we get older, or most of us do anyway. Those of you with great genes, who I'm very jealous of, that maybe it doesn't happen to you, But did anybody see an interview on, I think it was ABC News with Carrie Fisher? What's her name from Star Wars? Princess Leia. Leia. There's an interesting. If we get a chance, I'll play it at the end. It hits this topic, as a matter of fact. But at any rate, age and weight gain and so on and so forth. So at any rate, if I were now to take an individual and I'd say, okay, this 20-year-old weighs 150, 125 pounds, right? Well, now let's take a look. Now, what about a 30-year-old? I'm going to go in there, pick the next person. Next person happens to be 30. And as it happens, this 30-year-old happens to weigh, this guy was 150 pounds. This 30-year-old weighs 160 pounds. And this 40-year-old weighs 100 and, excuse me. Oh, I missed that, didn't I? This is, I'll call this 150. 100, 130, 150, 160, 180, 200. Let's do it that way. Okay, so this is 160, let's say, and this 40-year-old happens to weigh 170 pounds, and this 50-year-old happens to weigh 180 pounds, and this 60-year-old happens to weigh 190 pounds. As my randomly selected individuals measure their weight, we notice that their age, then we notice that their weight goes up as well. Okay, and each one of these points is the person's age, 20 years old, graphed with the person's weight, 150 pounds. So in other words, the value of x and y is 20, comma 150, right? X and y, just the way you would plot a normal graph on XY coordinates. Okay, so if I put all these lines together, you may have noticed that each 10 years added another, I think, 20 pounds. Did I add 10 pounds or 20 pounds, whatever it was, right? I added an exact amount that you would expect after each 10 years. It's linear. In other words, if I drew a line between these, it's a perfect straight line. Now, what that we would call that a correlation. There's a relationship or correlation. This is one of the rare instances in statistics where we're going to use a word in English almost the same way that we use it in statistics. There's a correlation or an association of some kind between age and weight. Okay, I'm making this, like these numbers are really never going to be this clean, but I'm just making this up. In this case, it happens to be a perfect correlation, right? Not only that, I can say to myself, if it's a perfect correlation, this line has a formula, right? That formula is going to be equal to, most likely, y is equal to some value times x plus another value. Y, remember, lines are equal to mx plus b, or whatever version of it you learned in school, where the m is the slope of the line and the b is where it crosses the x-axis, the y-intercept. We can write a formula here that represents this line. Since it's a perfect correlation, a perfect straight line, then we could say, well, if we got a person that's 35 years old, we can just plug in x for 35 for x and predict exactly what that person's weight is going to be. This never happens in real life. Never going to be a perfect correlation, right? What's going to happen really is that we're going to wind up with a situation where when we try and plot this, we're going to wind up with something that looks more like this. I'm going to put age down here. I'm going to put weight over here. And let's see, down, okay. These are all these individuals. Okay, I'm plotting the dot for each individual. Notice something in general about this? In general, the values tend to go up as age increases, weight increases. It's not a perfect line, right? Not a perfect straight line, but we can put a line here. We can put a line through here that is the best predictor of these values, where you could look at it a couple of ways. One way is to look at it in terms of, well, half of these lines are above this line, half of them are below this line, right? In reality, that's not really the case. The way that we're drawing this predictor line, right, or this best fit line, is that we're looking at how far away each one of these values is from this line. And we're looking at that in terms of the variability of all these different errors. All these distances are errors. And we want all of those errors, the value, the standard deviation for all of those errors to balance on one side and on the other side. So that's what we're doing. We're creating a line which is the best predictor for this, where the sum of all these deviations are equal, okay, above and below, where they balance out. Okay, so that line is, you could attempt to draw that line or calculate that line by hand, but most likely you're going to be working with a computer to determine what that line is. Well, there's a number of different kinds of situations you can get into here. And sometimes what you're going to wind up doing is you're going to wind up, I'm going to draw a few of these things here. Okay, sometimes, rarely, you're going to wind up with a correlation between two variables that's a perfect straight line, perfect correlation. We're going to work with a statistic called a Pearson's rho, or Pearson's correlation, right? And that R, or rho, is going to be a value which tells us how good a correlation that we have, okay? And the way that this is going to work is that when R is equal to 1, or when R is equal to -1, that's a perfect correlation, okay? Now, in this case, we have a perfect correlation. R is equal to 1. In this case, we have a perfect correlation, and R is equal to -1. What's the difference? One's positively correlated, one's negatively correlated. Okay, and let's say we have a situation where there doesn't seem to be any association at all. It's just random, right? What do you think R is going to be there? 0, exactly. So R is going to be 0. So the larger R is in the range 0 to 1, or 0 to -1, the larger the absolute value of R, the better the correlation. The better fit the line is to all the values, the smaller those residuals are. And that's what remember those little errors that we had, where a person's actual weight differed from what it would have been predicted by that line, how far they were from that line? That's called a residual. That error is called a residual. Okay, so the smaller the residuals, all of the residuals are, the closer that we're going to be to -1 or +1 here. Okay, now if we get an association that looks maybe something like this, that might be an R of, if it's positive, right? It's going to be a positive number. That might be an R of 0.25, right? And let's say we got something like this. Actually, it might be better than that. It might be 0.65, let's say. Okay, we got something like this where you can kind of see a relationship, but it's not very strong. That might be an R of negative point uh, 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 1, let's say. Okay, not very good correlation. Negative, but not a very good correlation. What about this? What do you think if I draw that, what do you think R is for that? Any other guesses? It's 0. It's 0. Why is it 0? How good a predictor is the X value on the Y value, right? They're all the same. They don't change, right? They never change. So there's no, as the X value goes up, the Y value always stays the same. So you can't, in other words, if the person's 20 years old or 60 years old, it's not a good predictor. Actually would have been easier if I switched the axes around.
So if there isn't a slope, it will always be 0.
Right, yes.
If there's the degree of the slope, that doesn't really have any correlation with
The degree of the slope,
correlation, right?
no. The degree is, in other words, you could have a very small slope, right, and have a very low correlation, right, or you could have a very big slope with a very tight correlation, a large R, right, or you could have a very large slope and have a very poor correlation, right? So they're independent,
Except for when it's slope equals zero. Then
right?
they are.
Yeah. Then there's no correlation. In other words, there's no association. No, what we're really looking for here is having one be see the association between one and the other. In other words, one changes, what kind of change do we get in the other? Okay, so let's take a look at what we're going to do with this now. Okay, so we're interested in that correlation. Now, when we talk about correlation, we don't care if the correlation is causative. We don't care if age is the cause of the weight gain. We're just looking for an association when we're talking about correlation. We don't care that, how'd that happen? We don't care that whether or not um, we've got it reversed, that weight gain causes you to get old, right? Which doesn't make sense. That's why we looked at it the other way, right? So um, we don't really care about causality. I'll give you an example of that. Let's say I told you, is there a relationship between the number of firemen that go to a fire and the amount of property damage at the fire? Would you say there's an association between those two? Yeah, right. Got a lot of firemen. It's going to be a lot of property damage. Are the firemen causing the property damage? No, it's not causal, right? The firemen are not causing the damage. It just happens that there's some other factor, like in this case, a lot of firemen is associated with a big fire, right? So there's an association, but it's not causal. Where the correlation is concerned, we don't care if it's causal or not. Matter of fact, I want to show you something interesting. Okay, I don't know if I think I did put this on Blackboard. Let's see. I need a link. Let me go here. There's a website where there's a statistician who really has too much time on his hands. This problem is, you'll see what I mean when we get there. It's really kind of interesting, though. Okay, let's see that. And yeah, it's down at the bottom there. Oh, I got to copy it here. Spurious correlations. Okay, these are correlations, but they're clearly not causative. Let me. I'll open. This is an article, really, in the Mirror, the newspaper in the UK. I can't get it to work. Okay, here. Just a coincidence. The more people eat cheese, the more people are killed by their veggies. This is a fellow that's examined enormous collections of data to look for associations between one thing and another thing. And sometimes he comes up with data that suggests that there's some association. Now, he's not showing it as a scatter plot where we're concerned, but he's showing the rates rather than the actual values for individuals. So let's take a look at this. Miss America, the age of Miss America in any given year correlates. Look how closely it is associated with murders by steam, hot vapors, and hot objects. Right? Okay. Per capita consumption of cheese and the number of people who died by becoming tangled in their bed sheets. Right? These are real numbers. Right? Obviously, one doesn't cause the other, but there's an association between the two of them. He has some really offbeat ones. And if you actually go to his website, I think I have his website there too. Let me see if I don't have it here. One graph suggests the amount of films Nicolas Cage appears in has a direct correlation with the number of people who drown by falling into a swimming pool. Right? Isn't that interesting stuff? So anyway, these are all spurious correlations. there's an association that you could show with numbers, but one clearly is not causing the other. Well, that's kind of where the difference between correlation, if there's some other interesting ones here. If you go to his website, you can spend a day there. It's amazing. But at any rate, the important difference now between correlation and regression is in regression, we're interested in using these associations as predictors. And if we're interested in using some of them as predictors, we really want to work with things that where the association is causal. As one changes, it really is associated somehow or other with the result in the other variable. Okay, so that's really one of the big things that's going to distinguish correlation with regression. So okay, so let's take a look at this. Let's see if we can't do a. I'm going to open up. Let's see what we have here. Arsenic and well water. I think I have a document that I created here. Okay, here we go. Okay, let's now there's a document on Blackboard that if you want to open up, you can take a look at it as well. We have 10 patients between 30 and 60 years old, randomly selected from patients in a long-term care facility. The data was obtained age and blood pressure. Oh, actually, age and blood sugar. Now, I'm going to make that change just like Levi did. I'll make the change on this document, but I'll forget and I'll use the old one anyway next semester, just like so. At any rate, blood sugar for each patient. So as patient age goes up, we suspect they're more likely to have diabetes. Their blood sugar will go up. Their fasting blood sugar level will go up. Okay, so we can solve this in SPSS very quickly and easily. I'm gonna open it in Excel first, just so that you can see that there are ways to do this in Excel also. Yay. Okay, let's see. Let me see if I got it on the desktop here. Oh, maybe I opened it already. Okay, all right, so here we go. Oh, no, I got that one. I think I got it on my desktop. The version I want is not on Blackboard. I think it has it on my desktop. Let me try opening it backwards. Okay, here we go. Okay, here's the data that we just looked at. I'm going to blow it up so we can actually see it. Okay, here's data that we just looked at. Age and blood sugar. This is patient number 1, patient number 2, and so on and so forth. 3, 4, 5, 6, 7, 8, 9, 10. Okay, so one of the first things that I can do in order to visualize whether there's an association between age and blood sugar is to create a scatter plot or plot these individual values. I'm going to highlight all of these. I'm going to go over to charts, pick a scatter plot, pick a simple scatter plot, and open it up. And let's see, does it look like there's an association? Kind of does, right? Okay. So these are all fake numbers. That's not an accident. I made the numbers up. So it would look like there's an association. Okay. However, we want to calculate that that value that examines how much in other words, if we fit this with a straight line, and in fact, if you hold down, if you highlight the values themselves, okay, and hold down Control or on PCs, right click on a Mac, Control click. One of the things that you have that you can check is no, I didn't do this right. Let's try this again. Control data line series add data line change reset to match. No, why am I having a problem with this? There it is. I still have it. No, I don't have it. Why am I not finding it? Reset the match. Select data. Data trend line. Format data? No. Oh, here, if you click on add trend line, okay, that is going to create that best fit line for you. Okay, and if you go into options when that comes up, can you see that up there? That's a little small, but I guess you can see it. There's also a option for displaying R squared. Remember, I told you R was our correlation, that number that's going to tell us how good a association it is. And there's also a display equation on the chart. We're going to get way ahead of ourselves here. We're going to display R squared, that number R squared, and we're going to display the line that represents this relationship. Okay, so that straight line that we have there, that straight line is represented by the formula y is equal to 1.7621, it's kind of precise, plus 17.476. Okay, so now let's take a look at that. Y is blood sugar, X is age, right? So really that, and we could have just written this as blood sugar is equal to 1.7 times age plus 17 and a half. I could have written it that way just as easily. Okay, so let's examine what happens when X is equal to zero. When X is equal to zero, that means age is equal to zero. That's my y-axis. That's what my y-axis is. So this line, if I were to extend it, it would cross the y-axis where x is equal to 0 at 17.47, hence the term y-axis. Notice they didn't extend this past the data. If you were to do it manually and extend it, it would cross just about there, just around 17 and a half, right? So it really is the y-axis. So if you know a point that it goes through and you know the slope, you've defined the line. If the point is here and it has to go through that point, the only other variable is the slope in defining what a line is. Okay, so they didn't extend this because when we talk about correlation and regression, we only work with the range of data, with the range of numbers that we have data for. In other words, in this particular study, the youngest person was 30 years old, the oldest person was 60 years old, right? So we don't make the assumption that we can use this formula to predict the way to somebody that's 15 or somebody that's 120 or blood sugar somebody that's 120. Which kind of makes sense, right? I mean, these are all adult, middle-aged to older adults, and you wouldn't want to use the same formula perhaps to predict blood sugars for infants or something like that. Wouldn't make any sense, right? Sometimes that y-axis doesn't make any sense. Sometimes that y-axis will be the age is minus 27, right? Meaningless, but that's okay. It's just where you're not really getting values at minus an age of minus 27. That's just where it happens to cross the y-axis. The real area you're working in, it's in real ages up here. Okay, so don't always expect that y-axis to have real meaning. So now the really interesting thing here for us is not so much where it crosses the y-axis, but the slope. What does that slope tell you? That slope tells you for every year a person ages, that's how much his blood sugar goes up. Okay? Well, maybe I made another correlation or regression. Maybe I did this also, not just for blood, not just for age, but I also did it for intake of carbohydrates, right? Average intake of a person's average intake of carbohydrates. And I did another regression. That slope came out to be 10. What would that tell you? That would tell you that eating a lot of carbohydrates has more to do with increased blood sugar than age does. Or maybe it's the relationship is the opposite. But you see how that slope is very important to us? That slope tells us which are the most important factors. Where should you intervene? Right? Should you intervene by cutting back on carbohydrates? Should you intervene by getting people to stop smoking? Should you and what would be the outcome of that intervention? In other words, if you were able to get people to cut back on carbohydrates, by 30%, what would you expect in terms of the average blood pressure of that population? That's the value of this. That's where this stuff becomes valuable to us. Okay, so we can use it as a predictor, and we can use it to decide where it would be important to have an intervention. So now, yes.
When you're using categorical variables, do you need to use parametrical method?
I'm sorry, say again.
When you're not using numerical variables and you're using categorical variables, can you do that regression?
Not this. We're only dealing with simple linear regression. This is
Okay.
strictly for numerical variables. You wouldn't use this for. You might say to yourself, well, what about ordinal variables? That's kind of numerical variables also. There are ways where we might be getting into that, right? How you might apply this to other kinds of data, but right now for simple linear regression, we're only doing it this way. Okay, so now remember we're only dealing with relationships that are linear, right? So for instance, if I go back here to, so if I can't get back to, where'd it go? Notebook, I just searched for it. Here we go. So if I go back here, not everything is a linear relationship. You might have some situations where the data, I think probably saw a couple of these, where it might look something like this, right? It's asymptotic, right? That's not a linear relationship, right? You might have some where it might look something like that, might even change direction, might look something like that, right? You might have some. Now, this relationship that we have here, right? Let's say that's equal to y is equal to 2x or something like that. Okay, 2x squared, let's say. Okay, so now we could actually take the log of these two relationships and say, okay, let's take a log of both sides here. Log of y is equal to the log of 2x squared, which is the same thing as 2 times the log of 2x, right? Am I right about that? I think I am. Okay, so now this is a linear relationship. A lot of times you can alter the formula to straighten this out. In other words, if this is a log scale now, you might find that the relationship is a linear relationship. So you can work around some of these issues with data that's not linear, and then you'll be dealing with other kinds of regression as well. Okay, so let's do a quick calculation here on my Excel spreadsheet, and you can kind of just watch me going through this. Now, some of the formulas that you were working with before, you were dealing with the average variability for the x values, for the y values, and for the combined x and y values. Okay, so you calculated on the slides, we calculated all these variables. So they're equal to the sum of all the differences squared, like we do sum of squares, divided by the sample size minus 1. Okay, I'm actually going to do this here. I'm going to get rid of the scatter plot first, just so that we have the vague idea this actually works. I'm going to lose the names age and blood sugar and just look at it as x and y. Okay, so if I were gonna try and calculate those values, the first thing I need to do is calculate x minus x bar. Okay, so x bar is going to be equal to the average of all of these values here, of the values for age. That's my x bar. And of course, my y bar is going to be equal to average here. I sure hope this has worked. I always feel better when this stuff actually works first time out. Okay, so now, now, first thing I'm going to need if I want to calculate the variability for x and variability for y is I need to know the difference between x and x bar. So that's going to be equal to the value for x minus x bar. And I'm about to hit enter, but before I hit enter, I'm going to put a $ in front of the I and the 13, so that when I copy it down, when I copy it down, it'll keep that value of 45.3. Okay, so there's x minus x bar, and I'm going to fill down. Okay, so that now, and then I'm going to do the same thing for y. I wonder if I just copy to the right. Edit, fill right. Okay, good. I think that worked right. I13, 30 minus, is that right? 30 minus, oh, excuse me. The mean was 97. Yeah, that looks right. Right. Okay, 75 minus 97.3 minus would be y minus y bar. Y is, no, something's wrong. Right. Let me do it again. Yeah, I'll do it again. Yeah. Okay, minus this, and I'll put the dollar sign in front of here. Something weird happened with the sign there. I'm not sure exactly what I did, but I don't have the time to figure it out right now. That's working now. Let it fill down. Okay, so now I'm going to take each of these values and I'm going to square it. X minus x bar squared, right? I'm going to do sum of squares as we usually do. Is equal to this value times itself. And I'm going to fill that down. And I'm going to do the same thing for y bar first. Equals this times itself. Okay, and I'm going to fill down. Down. Okay, and then I am going to take this value. I'm going to take this value. I'm going to add it all up. Oops. Equals sum. Parentheses. Okay, I'm going to do the same thing here. And I'm going to take these values, I'm going to divide them by n minus 1. This is equal to this value, sum of squares, divided by 9. Oops. And this is going to be equal to the sum of squares, divided by 9. Okay, let me see if I've forgotten anything there. Okay, so now, next thing I'm going to do is I'm going to take the square root of that. Okay, and I'll take the square root of this. Okay, this. And those values are going to be my standard deviation for x, for the x values, the average standard deviation for the x values, for the x value, and for the y value. Okay, now standard deviation for these cross values are going to be equal to, what's the formula for that again? Okay, it's going to be equal to x minus x bar 1 times y minus y bar 1. Okay. Okay, now that's going to be, I'm going to do that over here. Equals, okay, let's see, x minus x bar times, oh, oops, I don't want to be up there, equals x minus x bar times y minus y bar. Right? Divided by, I'm going to take that as if it's my square. I'm going to fill down. And I take the sum of all of those. Right? See the formula over there? I'm taking the sum. I'm taking the sum of all of those values. Okay. Then I'm going to divide that. Let's see what I got here. Then I'm going to divide that by this over 9. Okay, and then I'm going to take the square root of it. Okay, it's 13. So now I'm going to fill in my final formula there. And this is a version of the formula that you're using for R. R is equal to the total sum of squares, the total variability or standard deviation is equal to, R is equal to, oops, I didn't put it down there, did I? Let me put this down here so I can see it and work with it. Okay, let's put it here. Equals this. Okay, so R is going to be equal to total sum of squares, so a total at mean sum of squares. This this divided by this times this. Sum of squares for x and sum of squares for y. So I screwed it up. Was I supposed to divide by? I took the square root. The x minus x squared divided by the over n. Took the square root. Took the square root here. Did I take the square root there? I did take the square root there, right? Right.
Yeah.
Did you guys catch where I made a mistake?
I think you need a parenthesis on the last one.
You think?
Yeah. You need a parenthesis.
I think you're right. I think you're right. Yeah, because I've got to do the division. Well, that shouldn't matter, no? That shouldn't matter. Oh, you're right. It does matter. I guess that's r squared. Okay, and apparently that is equal to r squared. And r is equal to the square root of that. I still think I got it wrong, but I'm gonna move on. You get the idea. There is these funky little formulas that Levi puts on his lecture sheet, on his PowerPoints. They actually are the way you calculate this stuff. That was the point of my doing this, is that to show you that this is an actual physical calculation. If you wanted to, you could actually do this in Excel. Okay, and in fact, Excel actually has some shortcuts for you. You could see we could actually calculate r squared and the formula for regression. We could have calculated that just by using the functions on the scatter plot, the options on the scatter plot. Okay, so if we're approaching this from a perspective of, now you go to the community health data and you see you have information on how many ounces of, how many sugar sweetened drinks that a person drinks. And you also have information on how many cigarettes they smoke a day, right? And you want to say to yourself, well, gee, is there an association between the number of cigarettes a person smokes and how much coffee they drink, right? Or how much coffee they drink and how many cigarettes they smoke. I suspect there is, because there's an association, or how much alcohol people go to bar. You want to know something? Maybe that's not true anymore. If I had spoken to you about this 15 years ago, and I said to you, is there an association between the amount of alcohol someone drinks and how much they smoke? I would have said, gee, absolutely, because one of the things you'd see when you went into a bar is that there's a cloud of smoke. Everybody's having a drink, smoking while they have a drink. Or if they have a cup of coffee after a meal, they might be smoking while. In other words, the two behaviors related. Maybe not so much anymore, because you can't smoke in bars anymore. But maybe you are still drinking a lot. Maybe there still is association. But those are two numerical variables, right? The amount you drink, if you actually have the amount, and the number of cigarettes you smoke. Those are two numerical variables that you might be interested in seeing, analyze if there's an association between those two variables. Okay, so now what are you looking for when you look for that association? You're looking for the value of R, the correlation coefficient, Pearson's correlation coefficient. So what do you want from the value of R? What do you want R to be? You want it to be a big number or a small number? What's a good correlation? What's a bad correlation? You guys remember? Do you have value R? Yeah, positive one. You want R. You want R. You want R to be closer to positive one or negative one than to zero, right? Because the closer it is to those two values, the more the association between one numerical variable and the other numerical variable, the stronger the association between the two of them. But now, associations can be due to chance. What if I got an R of 0.3, right? Well, that suggests that there's a positive association, maybe not terrifically strong, but decent association between one variable and another variable. How do I know that that's not due to chance? I just happen to sample 20 people, and I just happen to find some that, as their age went up, something else went up. How do I know that's not due to chance? Well, I'm going to do what we always do, which is create do a hypothesis test. Okay, so let's talk about our hypothesis test. When we do a hypothesis test, we have a null hypothesis and we have an alternative hypothesis. What do you think our null hypothesis is going to be here? If there's no association, what is R equal to?
0.
Right, that's our null hypothesis. What's our alternative hypothesis?
R not 0.
Not zero. Exactly right. That's it. We're not predicting two-sided. We don't predict whether it's positive or negative. We just want to predict that. So associated with that, there is going to be an alpha that we're going to want to apply. In other words, what is our level of tolerance for an alpha error? Okay, in most cases, as before, it's equal to 0.05. Okay, so we want to calculate a probability of being wrong if we reject the null hypothesis. That's going to be our p-value. So we want our p-value to be less than 0.05 or less than alpha. If our p-value is less than 0.05, what can we say about the null hypothesis? We can reject it and accept the alternative hypothesis. So we got two things going on here. Number one is we have to have a p-value less than 0.05 so that we can reject the null hypothesis and say that the association is not due to chance. But we also would prefer to have as good an association as we possibly could. Now, as we were working on this, the other thing that Professor Waldron had mentioned is that, sure, we got R, right? There's an association from this value of a correlation called R. Okay, let's say that R is equal to 0.8. That's a pretty damn good association, right? Okay, now there's another value that we calculate when we do regression called R squared. Okay, so R squared, R is 0.8. R squared is 0.8 times 0.8 is equal to 0.64. What does that 0.64, that R squared, tell you about the association, about the errors that are going on there? What does it tell you about the association between one variable and the other variable? It tells you that, let's say it's a positive association, positive regression. As one value goes up, the x goes up, the y goes up also. It tells you that there's a certain amount of variability here, right? As one changes, the other changes. So amount of variability. It tells you that 64% roughly of the change in x, a change in y that's predicted by x is due to that is due to x, is due to that variable. So in other words, 36% is due to some other factors that we don't see here, right? So if we have a situation where that we can reject the null hypothesis, but our p-value is only 0.1, right? That our R value is only 0.1. Okay, when we multiply 0.1 times 0.1, it's 0.01. Well, that's not very significant, right? Because it may be true that we have an association, a weak association, but so little of the variability in the independent variable is due to changes in the dependent variable. It may not be an important association. Other things, there's 99% of the increase in blood sugar or blood pressure is due to something other than the increase in the value of the thing that you're associating with it. So even though it's significant statistically, it may not be important, in terms of like the real effect. Okay, so let's actually do a couple of these things using SPSS, because I think for the most part, when you work on your data, you're going to use SPSS or R, and if you have it or you have access to it here, most likely it's going to be R. So I'm going to switch computers for now, so that we can do that. Let me just go. I've been ignoring anybody that's online, so I just want to look back there and see if they're having issues there. Okay. You have a question? Okay. Well, okay, guys. You guys online. Does this make sense to you? You okay with this so far? I think that this is actually a situation where when you go back to the lecture, if you rewatch the lecture, that it'll fill in that you'll be able to fill in a lot of gaps here. That perhaps it would have been better to do this first and the lecture afterwards in this particular case, because it's kind of a complicated, complicated. These are complicated concepts, I think. Okay, so I'm going to switch over to the PC so that we can actually do some calculations. So hang on just a second. As I do that, okay, these, let me see, it's that one. Is that a, okay, so that should change. And I'm going to twist this around here so give us a better chance of being actually able to hear me as we're doing this. Okay, see what we got. No, did it switch? I don't think it switched. Hang on a second here. Yeah, I think it did switch. The only trouble is, oh no, I'm still presented, it looks like. Hang on a second. Okay, now that should work. Oh, good, okay. Show my screen. Okay, so you guys online should see the PC screen now and the mouse. Okay, good. So now I have a folder. This is a folder we copied over. And let's see. Okay, so here is that same data, age versus blood sugar, our bogus data, except this is an SPSS file. So I'm going to open that up instead of the Excel file. Same data, just a different file. Okay, and we'll wait here for the normal 20 minutes it takes SPSS to start up. There we go. Opened up pretty quick on this machine. Okay, there we go. It's the same data that we were working with. Okay, so now, first thing I want to do is examine this data to see if I think there is an association at all. So the easiest way to do this might be to create a scatter plot. So I'm going to go into graphs. I'm going to use legacy dialogues because I am a legacy. And I'm going to go down to scatter plot. There are others here. You can use, there are macros, and there's templates that you can use, and so on and so forth. It's a chart builder function. The simplest one is just go down to legacy dialogues and say I want to create a scatter dot, very similar to what you would do in Excel. Okay, a simple scatter dot, just X and Y axis. Okay, and I'm going to tell it that in the X axis, I'm going to put age, my predictor variable, and my Y axis, my dependent variable, I'm going to put in the Y axis. Now, for correlation, this wouldn't matter, right? We don't care which one is which. Okay, so I'm going to click OK, just so we can get a look at this thing and see what it looks like. Let's see what our scatter plot looks like. Well, it looks pretty good. Just as before, we got the graph in Excel, and it looks like we have a pretty good correlation now. Okay, so now I'm going to go back, and I'm going to go a step further here. I'm going to say, actually, I'm going to double click on this chart. I double click on this chart, an editor will come up. And one of the things that will come up is one of these symbols down here is a function to add a fit line. Okay, and similar to Excel, it adds that fit line for us, and in fact, it gives us the same value for the formula for that line as Excel does. The only difference here is it put the y-intercept in front of the slope, right? So we're 17.43, but it's the same value, right? And literally, if we were to fill in an age like 41 for X, then we would find a corresponding Y value that would be exactly on that line. Now, these fellas here are people that didn't fit that line exactly. In other words, this fella here is 44 years old, and his blood sugar was 115, let's say. Okay, and it would have predicted a smaller amount if we had used the formula. So that difference between the 115, between what we would have predicted on that line and his actual real blood sugar, is our residual, is our error or residual. And we could actually add in a function here, add plus and something like a little e or something like that for the error, for the residual. And and those numbers would then make this line fit perfectly for that one individual. Okay, so now let's take a look at this from the perspective of actually calculating this using regression in SPSS. Okay, let me get this out of the way. Okay, so now this time, I'm going to get this, close that. I'm going to analyze. I'm going to go to We have correlate and bivariate correlation, and that's what we're doing, right? Of course, this is bivariate correlation. We have two variables. Bivariate correlation, I'm going to put both of them in there again. Doesn't answer me which one's the dependent, which one's the independent variable, because it doesn't care. It's just looking for the association. And we're going to calculate Pearson's chi-square. I'll click OK, and I'll do it again so we can raise it up and see it. Okay, and here's our calculation of correlation. Okay, our Pearson's correlation is 0.821. That's the number I should have got when I did the cell calculation. I'll go over it and see if I can't figure out what I did wrong later on. Okay, so what's our null hypothesis? That there's no association between age and blood sugar, right? And what's another way of saying that? R is equal to 0. Our alternative hypothesis is that there is an association. Does it appear that there's an association? And is it a good association? Yeah, 0.821. R is 0.821. Can we reject our null hypothesis? Not yet, right? That could be due to chance. We have to know what the probability of getting that result if there's no association. What is that p-value? Or what SPSS called significance? It's 0.004. So now we can reject the null hypothesis. We have the magnitude of the association, and we also have evidence that we can reject that the null hypothesis and say that there is an association. Okay, so now we're going to take it to the